You may have heard a little bit about the new VITA 93 QMC standard, but what is it? Well, this time we're going to dive into some of the details and find out about that new form factor. Could you tell us about, what is the QMC form factor?
Well, the QMC itself, we're talking about usually a single QMC, which has a base size of 26 millimeters times 78.25 millimeters, with the standard component height of 4.7 millimeters, which is well known from PMC or XMC specification. Then we're talking about the PCIe Gen 6. It's capable of PCIe Gen 6 up to an X16 link, and can also be seamlessly integrated into managed systems. And the single QMC then comes with 40 IOs. And well, the QMC, we talked previously about scalability. It can scale up, and scalability is really important as it allows us to use the standard for a whole range of applications. So starting from simple I/O functionalities, a single QMC, up to more complex or highest complexity solutions on, for example, a quad QMC. And to elaborate that a little bit more, I said the single QMC has this base size of 78.25 millimeters times 26 millimeters and comes with 40 IO. And if you double that, we're talking about a double QMC. So we have the same width, which is still 78.25 millimeters, but we're then talking about 52.125 millimeters. So it just doubles the size. Then it comes with 80 IOs, so we're also doubling IO count. And when we're talking about the triple, you just triple the numbers of a single QMC. If you use a quad QMC, then we have all four, you quadruple it. And why is that so important? Because it basically allows us to build single function modules on the single QMC with like a UART design. And when it comes to highest complexity solutions, you can still use the QMC form factor, but just add more PCB area, more power, more host connectivity, and also more IO lines on the double, triple, and quad QMCs.
On a connector or a carrier board where you had, say, a quad, can you put 4 singles, 2 doubles, or you can only put 1 at a time?
Yeah, you can basically mix and match. If the carrier has 4 slots for QMCs, you can put 1 quad, 4 singles, like 2 doubles, a triple and a single, so you can just mix and match there. Of course, only limited by the QMC sides and the carrier connectivity.
Mark, are there other things that are affected by this flexibility in terms of layout?
Indeed. One of the things that we discovered while we were working on the standard was kind of the interest in non-rugged, but yet industrial types of applications. And in those cases, like a PCI Express finger card and edge finger card, could be a good carrier for QMC. And in that case, we realized that we could design a standardized IO connector module, if you will, to break out those IOs into kind of industry standard connectors, whether they be, DB9s or RJ45s or even fiber optic connectors or things like that. And so we've got a follow-on standard, 90.1, which is going to be defining that sort of IO paddle card, if you will. And so you can watch for that a little bit later in the year.
So what about the connectors, Matt? They're obviously rugged, but for industrial applications, are they going to be inexpensive?
Everybody always asks about the price right off, Bill. So I'm gonna skip that one, but we'll come back to it in just a moment. A good question about the connectors. Samtec has a long history of supporting mezzanine style connectors within VITA ecosystems. You know, we VITA 57, 1 and 4, VITA 42, VITA 88, VITA 93 is just an extension of that. And, you know, historically, we've used what we call our C-rate product. It's an open pin field array. It's a 1.27 millimeter. It's very rugged. There's various stack heights. Various orientations. But it has its limitations because it's large. There's a finite speed that you can get from a data rate standpoint. So, you know, Samtec started looking at that probably, 5 to 7 years ago and say, we really need a next generation open pin field array that's smaller, denser, faster. And the end result of that is a product family that we call Accelerate HD that has all the benefits of C-Ray. It's open pin field array, which means any one signal or any one pin can be power, high-speed differential, single-ended, analog, whatever the case may be. But it's a 0.635 millimeter pitch. So it's very dense. It's also very thin. So this made Accelerate HD the ideal candidate for the mezzanine connectors within QMC. Because of the dense design, the slim design, and because of the advanced SI that we put into the design of the contact system, we can get data rates PCI 6, 64 gigabit per second PAM4 through the connector. And that's one of the reasons that the QMC committee chose the Accelerate HD connectors for the application. We talked earlier too about variability in stack height. It was a key design element of QMC, and the fact that Accelerate HD, our interconnect solutions, are flexible in terms of stack height. You know, we can support 5 millimeter, 9 millimeter, 11s, 14 and 16 and beyond within the family, and several of those are within the spec. We're really happy that the QMC the technical working group, the committee, chose this solution, and we're looking forward to supporting new designs, new applications as QMC gets adopted by the industry.
Were you going to come back to pricing? Because industrial is one of those applications where I think this is going to be ideal. There's a big lack of rugged expansion, and it looks like it could address that. 'Cause we were also talking, about using carrier cards that might be industry standard cards, PCI cards, for example.
Yeah. So what I would say to that is I'll answer that generically, Bill, because obviously every pricing engagement is based on volume and things like that. Accelerate's been on the market for a while. It's a mature product line. You know, it has volume behind it. It's not just launching. And as the scale of the Accelerate family, it's adopted across multiple SOM standards, both within industry standard ecosystems and within ad hoc solutions, without mentioning any names here. So it's very cost effective for the application. So we can work with customers to be strategic. We understand the opportunities that QMC provides, and we can provide a cost competitive solution to meet their needs.
Excellent. It sounds like it's already used in a lot of industrial applications. So this is just yet one more.
Yeah.
Okay.
Yeah.
Let's talk a little bit about cooling, because a lot of standards just talk about form factors. They don't talk about things like cooling. Mark, could you tell us a little bit about how this design, the standard, incorporates that?
Sure, I'd be happy to. So as I mentioned in the previous video, the kind of the driving force for us creating the QMC standard was the need to have an IO expansion capability for VNX Plus. VNX Plus modules are quite small, too small for XMC or other mezzanines that are available that had both a host side connector and a standardized IO connector. And inherently, VNX Plus is a conduction cooled platform. And so we needed to have a QMC or a mezzanine IO that could support conduction cooling. So from the beginning, we designed this with kind of very exacting requirements, if you will, for being able to support cooling the mezzanine through cooling structures in the carrier through conduction. But like I mentioned in passing earlier, air-cooled applications became pretty obvious as well, and we wanted to be able to support air-cooled applications. And so what we did is we crafted the standard so that the kind of the stacking heights, if you will, are very, very closely defined so that you can either have a conduction cooling structure, or you could have an air cooled like fin array or pin array or something like that, or just no cooling metal at all, and just leaving it open to the air. If it's a relatively low power application, you're flexible as far as to deploy what your needs are.
Mhm. Jan, could you sort of comment on the boards that you've been putting together? How are they being provided in terms of cooling? What options are you providing your customers?
So and my focus is on conduction cooling because that tends to be most of my business. The cooling structures are like 100% driven by the carrier, and in fact we were, other than the dimensions, we don't prescribe anything with regards to what the carrier has to do to provide the cooling. We wanted to make sure that the market had room to innovate and could come up with their own clever structures for moving that heat around in sometimes very difficult or tight spaces. And so I don't want to go into too many details because it's still a new market, and we want to keep a little secrets, but it is proving to be kind of an interesting problem.
Another area which sort of complement to this is power. You need to cool things down, but you need to also provide sufficient power for some of these new chips, especially say AIs and GPUs. Could you talk a little bit about that?
Sure. The pin grab that we chose for QMC actually provides plenty of power, probably more power than you can reasonably cool in such a small form factor. In fact, I've got my numbers here. Maximum is 7.92 watts for 3.3 and 21.6 watts at 12 volts. So that's quite a bit of power for a single QMC, which is quite small. And then naturally, the double, triple, and quad, you increase the number of pins, you increase the amount of power that's available. So it's really going to be kind of more, that power is not going to be a problem. But cooling with that amount of power, that's where your challenges are going to be. And I think that's where kind of the interesting innovations are going to happen.
Maybe I could just comment on that for a second too, from a connector standpoint. I think that illustrates too the flexibility of the interconnect that the QMC consortium or the technical working group chose, because the current carrying capabilities per pin are rather high for how small it is. So that capability, that flexibility within the interconnect also adds to the power budgets available within QMC.
Well, to wrap up, let's talk a little bit about what are some of the advantages of this form factor that you see are going to be of benefits to designers? Jan, why don't we start with you?
Yeah, of course. Well, I think one of the biggest benefits for designers and for users is that, well, probably more for users, to be honest, but it is that the defined concept of the QMCs ensures interoperability between vendors. So you have one carrier, and no matter which vendor you choose, like your QMCs from, they will all fit and work. And this is what the current concept of the QMCs ensure. And I think that's a big plus for the end customer or the system integrator in the end.
I think just the portability of the platform. FMC is going a lot of different places. XMC is going a lot of different places. Continuing that trend within the VITA ecosystem, QMC is going to go into a lot of places. So if I'm a carrier card vendor, or if I'm a QMC IO vendor, that's going to allow for unlimited options. Almost you're limited by the imagination of the system designer. And if you're an OEM, obviously that simplifies and quickens time to market as the modules become available.
Mark, you get to wrap it up.
All right. So just to build a little bit on what Jan and Matt said, because I agree 100% with what they said. The fact that you've got a standard form factor that was so carefully crafted and well thought out by a great team of people on the working group, to be able to have that level of performance and scalability in something that is like guaranteed to work regardless of what vendor you choose from the carrier or from the QMC side, is really going to be, it's really remarkable, and I think it's really going to show when these products start really hitting the marketplace.
Great. Well, thanks very much. Everybody stay tuned for more on VITA QMC.